Given, two integer arrays nums1 and nums2 whose entries are digits 0 through 9, and an integer k, rule, build a number of exactly k digits by choosing digits from both arrays. You may skip digits, but the relative order within each array must stay the same. Output, the k-digit array that forms the largest possible number, most significant digit first. Example 1, pick 5 digits total. 9 from the second array is the strongest start. Next, 8 from the second array beats anything left in the first. Then 6 and 5 from the first array, in their original order, and finally 3 from the second. That gives 9, 8, 6, 5, 3. Example 2, k equals 5, so we must use every digit from both arrays. Keep 6 and 7 from the first array and 6, 0, 4 from the second, then merge them in order while preserving each array's order. The largest merge is 6, 7, 6, 0, 4. We are handed two arrays of digits and tasked with creating the largest possible 3-digit number. The twist is that we must preserve the relative order of the numbers exactly as they appear in their original arrays. Trying to make decisions across both arrays simultaneously creates a chaotic matrix of choices. To tame this problem, we need to split our responsibilities. What if we decoupled the two arrays completely? If we define a fixed budget for each array, saying we will take exactly I digits from the first array and exactly k minus I digits from the second, they stop competing. Since our constraints are small, we can just systematically test every single valid split combination one by one. This reduces our problem to a clear, isolated subtask. Given a budget, how do we select the absolute best standalone sequence from a single array? Let's test our second split option where we want 1 digit from the first array and 2 from the second. To pull the best digits, we use a monotonic stack. Watch the first array, 3 enters, but when the massive 9 arrives, it kicks the smaller 3 right out of the stack. This leaves us with a pristine candidate, 9 in a 1-digit stack. We run the same engine on the second array, filtering it down to 8 and 3. The monotonic stack has cleanly generated our 2 isolated champions for this budget. Now that our individual subproblems are solved for this budget, our next milestone is to merge these 2 stack outputs back into a single 3-digit number. We drop a pointer at the head of both lists and compare them. Since 9 is larger than 8, we pull the 9 first. Then, the remaining 8 and 3 fall right into place behind it, giving us a combined result of 983. To be absolutely sure we find the maximum possible number, our code must evaluate the other budgets too. For split C, where we demand 2 digits from the first array and 1 from the second, our monotonic stack leaves us with 3 and 9, and 8. When merged regularly, 8 takes the lead, giving us 839. Every budget split yields a final merged number. We compare all 3 and keep only the best. Split B gives 983, the largest. But what happens if our pointers ever hit an exact tie during a merge? If we have an 8 on both sides, a blind guess could ruin our sequence. To break a tie flawlessly, our algorithm looks into the future. It compares the entire remaining suffixes of both arrays, treating them like words in a dictionary. Because the future path of 89 is greater than 82, the first stack wins the tiebreaker, and we confidently pull its 8 first. This look-ahead step ensures our heaviest values always claim the front seat. To ensure our engine never fails, it handles boundary conditions using 2 simple rules. To prevent going under budget, the stack uses a protective shield. It only allows a smaller digit to be kicked out if our total remaining pool of elements is strictly greater than our budget. To handle going over budget, which happens when a sequence keeps increasing without any deletions, we don't need complex mid-loop logic. We simply let the digits accumulate, and cleanly slice the stack down to our exact budget size at the very end. To implement this solution, we initialize our master control panel. We create an empty tracker to hold our absolute best combination. Then, we set up a loop to iterate through every valid digit budget split between our two input arrays, ensuring the total count always equals k. We write a helper function to extract the largest standalone sequence for a given budget using a monotonic stack. We track a drop allowance, the number of elements we can safely discard without falling short of our budget. As we loop through the digits, if we see a larger number and still have drop allowance left, we pop the smaller number off the stack and decrement our allowance. If an array's digits are strictly decreasing, our loop won't drop anything, leaving the stack over budget. To handle this cleanly, our function returns a sliced copy of the stack, truncated exactly to our requested budget size. For this budget iteration, our helper perfectly delivers candidate 9 from array 1 and candidate 8, 3 from array 2. With our standalone candidates ready, we pass them to our merge function. Instead of a simple element comparison, our merge loop compares the entire remaining suffixes of both stacks. Whichever stack has the greater future path wins the round, and we pull its leading digit forward into our merged result. For our current candidates, this cleanly builds out the number 9, 8, 3. Let's see why this look-ahead condition is so elegant. When both pointers face a tie, like an 8 on both sides, the standard greater than operator evaluates the entire remaining arrays like words in a dictionary. Because 89 is greater than 82, the comparison resolves in favor of stack 1. It pulls its 8 first, perfectly preserving our heavy digits in the front. Back in our master loop, we compare the merged result of our current budget split against our standing global record. If it's larger, we update our master tracker. After iterating through all valid budgets, our control panel holds the definitive maximum combination. All that's left is to return it. By orchestrating a monotonic stack engine with a look-ahead merge, we've broken down a massive constraint problem into a flawless, sequential victory. Let m be the length of nums 1, n the length of nums 2, and k the number of digits to pick. Time is O of k times m plus n squared in the worst case. We try order k budget splits, and each split runs a linear monotonic stack pass plus a suffix-aware merge that may compare up to k remaining digits per step. Auxiliary space is O of m plus n for candidate subsequences and merge buffers. Full pseudocode for create maximum number, a main split loop plus 2 helpers. We will walk each line on 3 short frames. Top-level routine, try every valid budget split and keep the best merged number. Start with no answer, we will replace it when a split beats the record. Loop I, digits taken from nums 1, k minus I come from nums 2. Extract the best length I subsequence from the first array. Extract the best length k-i subsequence from the second array. Merge the two candidates with suffix look-ahead comparison. If this merged number is lexicographically larger, promote it. Overwrite best with the new champion split. Return the maximum combination after all splits are tested. Frame 2. The monotonic stack helper that extracts the best subsequence for a fixed budget. Helper, largest length budget subsequence from one array using a monotonic stack. Empty stack before scanning digits. Drop allowance counts how many digits we may discard. Scan the array left to right. While a larger digit arrives and drops remain, pop smaller tops. Remove the smaller digit and spend one drop. Push the current digit onto the stack. Trim or return the first budget digits as the candidate. Frame 3, the suffix look-ahead merge that combines two candidates. Helper, merge two candidate lists into the largest valid combined sequence. Accumulate output digits here. Continue until both input lists are exhausted. Compare entire remaining suffixes, not just the heads. This is suffix compare on remainders, Use a built-in operator if your language has one, otherwise a small helper routine. Take the leading digit from the list with the greater suffix. Otherwise take from the other list. Append that front digit to merged. Return the fully merged candidate for this budget split.